In 1981, a team of astronomers pointed a telescope toward the constellation Bootes, expecting to find what every previous survey had found: galaxies. Hundreds of them, clustered together the way galaxies almost always are. Instead, they found almost nothing. For a stretch of space so large that light itself would need more than 300 million years to cross it, there were only a handful of galaxies scattered where thousands should have been. Astronomer Robert Kirshner, who led the discovery, later joked that if you drove a spaceship straight through the middle of it at the speed of light and fell asleep for the entire trip, you still would not miss much. His team nicknamed it the Great Nothing. That region became known as the Bootes Void, and it turned out to be just one small example of something far bigger. Roughly 80% of the volume of the observable universe is not filled with galaxies, stars, or planets. It is filled with almost nothing. Vast, dark, nearly empty regions of space called cosmic voids, stretching for hundreds of millions of light years in every direction, containing so little matter that some astronomers describe them as the closest thing nature has ever built to true emptiness. For anyone interested in the search for life in habitable worlds, this raises an uncomfortable question. If most of the universe is essentially empty space, what does that mean for the odds of finding anyone else out there? And if a civilization happened to evolve inside one of these voids, what would their entire understanding of the universe even look like? This is the story of the emptiest places ever discovered, how they were found, why they exist, and what they reveal about how narrow our window for understanding the cosmos actually is. Before we go any further, if you have not subscribed yet, now is a good time. We cover stories exactly like this one, the biggest structures in the universe and what they mean for the search for life beyond Earth, every single week. To understand why voids exist in the first place, you have to understand the overall shape of the universe on its largest scales, something cosmologists call the cosmic web. If you zoom out far enough, past individual stars, past galaxies, past even clusters of thousands of galaxies, a strange pattern starts to emerge. Matter in the universe is not spread out evenly. It is arranged into long filaments of galaxies that stretch across space like threads, connected at dense nodes called galaxy clusters, and separated by enormous gaps where almost nothing exists at all. Those gaps are the voids. Picture a kitchen sponge. The solid material of the sponge forms a connected, tangled structure of walls and strands, but most of the sponge's actual volume is empty holes. The universe looks remarkably similar on the largest scales humans have ever mapped. Galaxies are not scattered randomly like sand thrown across a table. They are arranged along this vast underlying scaffold, and the empty holes between the strands can be almost impossibly large. Mapping this structure took decades. In the 1980s and 1990s, astronomers began systematically measuring the distances to thousands of galaxies using a technique called redshift surveys, essentially using the stretching of light from an expanding universe to calculate how far away each galaxy actually is. The Center for Astrophysics Redshift Survey was one of the first major efforts, and it produced a shocking result. When researchers plotted galaxy positions in 3 dimensions, they did not see a uniform haze of galaxies filling space evenly. They saw a web. Dense walls of galaxies, later named things like the Great Wall, sitting next to regions that were almost completely empty. Later surveys made the picture even clearer. The 2-degree Field Galaxy Redshift Survey and the Sloan Digital Sky Survey mapped millions of galaxies across the sky, and computer simulations built from these maps. Projects like the Millennium Simulation and later the Illustris and Eagle simulations showed how this cosmic web forms. It starts with tiny fluctuations in the density of matter left over from the earliest moments after the Big Bang. Fluctuations so small they are measured in the cosmic microwave background as differences of only a few parts in 100,000. Over billions of years, gravity amplified those tiny differences. Regions that started out slightly denser than average pulled in more and more matter, growing into galaxies, clusters, and the filaments connecting them. Regions that started out slightly less dense than average did the opposite. They kept losing matter to their denser neighbors, becoming emptier and emptier over cosmic time, until they became voids. So voids are not simply blank spots where nothing happened. They are the result of an active, billions of years long process of gravitational sorting, where matter drained away from underdense regions and piled up somewhere else. The universe essentially rearranged itself, concentrating almost everything interesting into a thin web of structure, while leaving most of its volume nearly untouched. Now for the scale of this emptiness, because the numbers involved are difficult to fully process. A typical cosmic void measures somewhere between 200 and 700 million light-years across. The Bootes void that started this story spans roughly 330 million light-years. Based on the average density of galaxies elsewhere in the universe, a region that size should contain somewhere around 2,000 galaxies. Astronomers have found fewer than 60. To put that in perspective, imagine a stadium built to hold 2,000 people. And when you walk inside, you find fewer than 60 scattered across the entire structure. That is roughly the level of emptiness we are talking about, except stretched across a volume of space so large that our entire Milky Way galaxy, at 100,000 light-years across, would look like a grain of sand dropped into an empty football field. And the Bootes void is not even the largest one discovered. In the constellation Eridanus, astronomers identified an even larger region of underdensity, sometimes called the Eridanus supervoid, stretching close to 1.8 billion light-years across. This particular void has drawn intense scientific interest because its location roughly lines up with something called the cold spot, an unusually cold patch discovered in the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the entire sky. Some researchers propose that an enormous void along our line of sight could explain the cold spot, because light traveling through a region with less gravitational pull loses a small amount of energy differently than light traveling through denser regions, a subtle effect called the integrated Sachs-Wolf effect. The debate over whether this supervoid fully explains the cold spot is still ongoing, but the fact that a single region of relative emptiness might be leaving a fingerprint on the oldest light in the universe tells you just how significant these structures are. There is an even stranger possibility much closer to home. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie proposed that the Milky Way itself might sit inside the edge of a large cosmic void, now often called the Keenan-Barger-Cowie void, or simply the local hole. Later research, including a detailed 2020 study led by Benjamin Hochheit and further work by Indranil Banik and Pavel Krupa, estimated that we may be living inside a region roughly 1 billion light-years across, where the density of galaxies is around 20% lower than the cosmic average. If this is correct, it could help explain one of the most stubborn problems in modern cosmology, a discrepancy known as the Hubble tension. Different methods of measuring how fast the universe is expanding keep producing slightly different answers, and nobody has been able to fully reconcile them. One explanation is that living inside a large underdense region would locally distort our measurement of cosmic expansion, because matter outside our void would gravitationally pull on everything inside it in a way that mimics extra acceleration. In other words, the very structure this video is about, the emptiness of cosmic voids, might already be quietly warping some of humanity's most fundamental measurements of how the universe behaves, right from where we are standing. Now here is where it gets genuinely strange, because voids are not perfectly empty. Even the darkest regions of space contain something. Hydrogen gas, diffuse and thin, spread across unimaginable distances at densities so low they are almost impossible to recreate in any laboratory on Earth. This diffuse material is part of what astronomers call the intergalactic medium, and within voids specifically, it takes the form of the warm-hot intergalactic medium, gas heated to hundreds of thousands or millions of degrees by the gravitational churn of structure formation, yet spread so thin its density can be less than 1 atom per cubic meter. For decades, this diffuse gas was considered one of the missing pieces of a much bigger puzzle known as the missing baryon problem. Cosmologists could calculate, based on the physics of the Big Bang, roughly how much ordinary matter, protons, neutrons, and everything made of them should exist in the universe, but when astronomers added up all the matter they could directly observe in stars, galaxies, and glowing gas clouds, they consistently came up short by roughly half. Where was the missing matter hiding? Part of the answer came from an unexpected source. Fast radio bursts, brief and extraordinarily powerful flashes of radio energy from deep space, travel billions of light years before reaching Earth. As that light passes through the diffuse gas scattered throughout voids and the wider cosmic web, it gets slightly delayed and dispersed in a measurable way. In 2018 and the years following, researchers used this dispersion effect, sometimes called the Macquart relation after astronomer Jean-Pierre Macquart, to essentially weigh the invisible gas sitting in the space between galaxies. The missing matter was not missing after all. It was spread so thin across voids and filaments that it had simply been invisible to older observation methods. This matters enormously for understanding voids properly. They are not regions of absolute nothing. They are regions where the scaffolding of gravity never managed to concentrate matter into stars and galaxies. A handful of atoms drift for millions of years without colliding with another atom. It is the closest thing the observable universe offers to a true vacuum, and yet even this is filled with faint traces of the same hydrogen that eventually built every star, planet, and living thing anywhere else. So what about the handful of galaxies that do exist inside these vast empty regions? Astronomers have studied them closely, most notably through a long-running project called the Void Galaxy Survey, led by researchers including Catherine Krekel and Rianne van de Weijgaard, using telescope time on some of the world's most powerful instruments to examine galaxies sitting deep inside cosmic voids far from any cluster or filament. What they found was fascinating. Void galaxies tend to be smaller, gas-richer, and more dominated by dark matter relative to ordinary matter compared to galaxies living in denser environments. They form stars more slowly. They rarely experience the galaxy mergers and close gravitational encounters that shape and often disrupt galaxies elsewhere. The kind of violent interactions that trigger bursts of star formation, distort spiral arms, or funnel gas into central black holes. Because void galaxies are so isolated, they evolve almost undisturbed, essentially frozen in a more primitive state compared to their crowded cosmic neighbors. Researchers sometimes call them pristine laboratories, galaxies that let us study what star formation looks like without the constant gravitational chaos most galaxies experience. But this isolation carries a consequence that matters directly for the search for habitable worlds. Heavy elements, the carbon, oxygen, nitrogen, iron, and everything else beyond hydrogen and helium that life as we know it depends on, are forged inside stars and scattered into space through supernova explosions and stellar winds. Galaxies with fewer stellar generations, fewer mergers, and slower overall evolution tend to have lower concentrations of these heavy elements, something astronomers call lower metallicity. A void galaxy that has spent billions of years quietly drifting in near isolation may simply not have built up the chemical complexity needed to form rocky, Earth-like planets in large numbers, let alone the more complex molecules associated with biology as we understand it. This leads to a genuinely strange thought experiment. Suppose intelligent life somehow did emerge on a planet inside one of these void galaxies, against the odds created by lower metallicity and sparse stellar history. What would their view of the universe actually look like? Their night sky would be almost unimaginably empty compared to ours. From Earth, even without a telescope, the night sky is dense with stars. And with a telescope, astronomers can observe thousands of other galaxies within relatively short exposure times. Evidence that immediately points toward a vast, structured cosmos filled with billions of other galaxies. A civilization evolving deep inside a void, hundreds of millions of light years from the nearest galaxy cluster, would look out into a sky that is, for enormous stretches in every direction, essentially black. Their nearest galactic neighbor might sit so far away that its light would take hundreds of millions of years to arrive, appearing as nothing more than the faintest possible smudge, if it were detectable at all with early observational technology. Their entire concept of cosmology, the idea that the universe is built from galaxies clustered into a vast interconnected web, might take enormously longer to even become apparent, simply because the evidence would be so much sparser and so much farther away. And there is a far stranger version of this thought experiment, one that does not require imagining a hypothetical alien civilization inside a void at all, because it applies directly to us and to every future civilization that will ever exist here on Earth. In 2007, physicists Lawrence Krauss and Robert Scherer published a paper that unsettled a lot of people in the cosmology community. The universe's expansion is not just continuing, it is accelerating, driven by the mysterious force known as dark energy. Because of that acceleration, every galaxy outside our immediate local group, the collection of galaxies gravitationally bound to the Milky Way, including Andromeda, is drifting away from us faster and faster. Eventually, roughly 100 billion years from now, according to their calculations, every one of those galaxies will have accelerated beyond what is called the cosmological horizon, the point past which their light can never again reach us, no matter how long we wait. At that point, any civilization looking out from the local group, by then likely merged into a single giant elliptical galaxy combining the Milky Way and Andromeda, would see nothing beyond their own galaxy, no other galaxies, no expanding cosmic web. Even the cosmic microwave background, the leftover light from the Big Bang that we currently use as our single strongest piece of evidence for how the universe began, will have stretched and faded beyond any possible detection. A scientist in that unimaginably distant future, using instruments far more advanced than anything we have today, would look at the universe and reasonably conclude that they live in a small, static, unchanging island of stars, alone in an otherwise empty cosmos, with absolutely no observational evidence that a Big Bang, an expanding universe, or any of the other galaxies we currently study ever existed at all. In other words, every future intelligent species born after that point will effectively live inside a void, not because of where their galaxy happens to sit today, but because time itself will have carried all the evidence away. We are living right now during one of the only eras in the entire history of the universe when cosmology is even observationally possible. Krauss and Scherer described it almost like an incredibly narrow observational window, cosmically unique, and we happen to exist inside it. That reframes everything about the voids we started this story with. They are not just distant curiosities sitting hundreds of millions of light years away in the constellations Bootes or Eridanus. They are a preview, a glimpse of the kind of isolation that dark energy is slowly building for every galaxy in the universe, including our own, stretched out over cosmic timescales that make even the age of the universe so far look brief by comparison. This also changes how astronomers think about the search for life itself. Habitability has traditionally been framed almost entirely in terms of a single star system, whether a planet sits in the right orbital zone for liquid water, whether it has the right atmosphere, the right mass, the right kind of star. But voids and their opposite, dense galaxy clusters, introduce another layer to that question entirely, something researchers now sometimes call cosmic habitability, or the galactic habitable zone extended to the scale of the cosmic web itself. Being inside a dense cluster of galaxies exposes a planet to more frequent supernova explosions, more gamma-ray bursts, more disruptive close encounters between galaxies, all of which can sterilize life or destabilize planetary systems over long timescales. Being inside a void offers the opposite. Fewer catastrophic events, more stable, undisturbed conditions over billions of years, precisely the calm, isolated environment that complex life might actually need to develop without being wiped out by a nearby cosmic explosion. The same isolation that makes void galaxies chemically primitive may also, ironically, make them safer places for whatever life does eventually emerge there to survive uninterrupted for a very long time. So the very structure that seems to work against habitability by starving void galaxies of the heavy elements life requires might simultaneously be protecting whatever life does eventually form there from the violent cosmic events that make denser regions more dangerous. Nobody currently knows which effect wins out over cosmic history. It is an active area of ongoing research. Modern missions are being built specifically to map this structure with far greater precision than ever before. The European Space Agency's Euclid mission, launched in 2023, is designed to chart the distribution of billions of galaxies across enormous volumes of space, tracing the cosmic web in unprecedented detail, all in an effort to better understand dark energy and dark matter, the two invisible forces that shape this entire structure in the first place. Ground-based facilities like the Vera Rubin Observatory will photograph the visible sky repeatedly over the course of a decade, cataloging voids and providing the long-term data needed to test whether the local hole hypothesis is correct. Even the way light bends as it passes near or through voids offers scientists an independent tool for studying them. A phenomenon called weak gravitational lensing, where the paths of light rays are subtly distorted by nearby gravity, works differently around voids than around dense clusters, effectively demagnifying light rather than magnifying it. By measuring these subtle distortions across huge numbers of galaxies, researchers can map the invisible dark matter scaffolding of voids directly. All of this research, mapping the cosmic web, measuring the intergalactic medium, studying isolated void galaxies, testing the local hole hypothesis, ultimately connects back to the exact same question this channel keeps returning to. How rare or how common are the conditions that allow life to exist anywhere in this universe? Understanding the structure of cosmic voids is not simply a matter of cataloging empty space for its own sake. It shapes how astronomers calculate the odds of habitable planets forming across cosmic history, how heavy elements get distributed unevenly throughout different regions of the universe, and how safe or dangerous different galactic environments are for whatever life manages to take hold within them. Return for a moment to that image from the very beginning of this video. A team of astronomers in 1981 pointing a telescope toward the constellation Bootes, expecting galaxies, and instead finding a silence so vast it would take a beam of light more than 300 million years to cross it. That discovery did not just reveal one strange region of the sky. It cracked open an entirely new understanding of how the universe is built, mostly emptiness, threaded through with a comparatively thin web of galaxies, stars, and, as far as we currently know, exactly one small blue planet where someone eventually looked up and started asking questions. Every void galaxy drifting alone in the dark, every future civilization that will eventually watch the rest of the universe fade permanently beyond reach, and every one of us right now, living inside this narrow, temporary window where the entire cosmic structure is still visible and still measurable, are all part of the same story. A universe built mostly out of nothing, with life, wherever it exists, occupying an almost unimaginably small and fleeting fraction of both its space and its time.